The observable universe spans approximately 90 billion light-years. It's reasonable to assume the unobservable portion is significantly larger. The cosmos is so vast it surpasses human comprehension, at least for now. However, some theories suggest the universe might be far smaller than we perceive. This is because the observable universe's size is limited by the distance light has traveled since the Big Bang, roughly 13.8 billion years ago. The actual size of the universe, including the unobservable portion, is a subject of ongoing debate and research. Estimates vary greatly, with some suggesting a diameter exceeding 20 trillion light-years, a figure far surpassing previous estimates and indicating immense scale. Consider the observable universe's vastness. Given the relatively small amount of matter detected in the explored regions, a significant portion of space must be essentially empty. Looking out into space reveals immense stretches of seemingly empty void. But what if the entire universe were contained within a single atom? This sounds absurd, but the idea, while bordering on philosophical speculation, isn't entirely implausible. All matter comprises atoms, the fundamental building blocks of our perceived reality. Atoms are so minuscule that even the most powerful optical instruments can't directly visualize them. We lack a definitive understanding of their precise appearance, relying on inferences from scientific data and quantum mechanics. In actuality, atoms themselves are composed of even smaller subatomic particles: neutrons, protons, electrons, and quarks. A typical adult human body contains approximately 7 octillion atoms. Atoms, despite their tiny size, possess a complex internal structure. This structure gives rise to the intriguing concept of a micro-universe. The familiar model of an atom, dating back to Ernest Rutherford's 1911 planetary model, depicts a nucleus orbited by electrons. While this model simplifies the complex quantum reality of electron behavior, it remains a useful and generally accurate representation. The behavior of electrons is more accurately described by quantum mechanics, not classical mechanics, but the analogy to a solar system, though not perfectly accurate, is a helpful one for visualization. Could the similarity between atomic structure and solar systems be a mere coincidence, a consequence of universal physical laws? Or does this resemblance suggest something more profound? The number of electrons in the universe is an unfathomably large number that cannot be accurately computed. But consider this. The one-electron universe hypothesis proposed by Richard Feynman postulates that only one electron exists, moving through space-time so rapidly that it appears as countless electrons. This single particle supposedly forms the entirety of what we perceive as the universe. Though not widely accepted, this hypothesis illustrates the challenges of understanding the universe's fundamental structure. The principle of electron indistinguishability, the impossibility of distinguishing one electron from another, makes this hypothesis impossible to definitively disprove experimentally. The concept of size is itself relative. Our world is tailored to our scale. However, nature presents vastly different scales. Mountains seem enormous to us. Planets are colossal beyond comprehension. Ants perceive their world differently. In their microscale, everything is vastly larger proportionally. Compared to cosmic objects, we are not just microscopic. We are infinitesimally small. This vastness, as explored by authors like H.P. Lovecraft, highlights humanity's insignificance in the face of the infinite cosmos. What if our universe could fit on a pinhead? What if our solar system and everything we experience exist within an atom of a larger reality? This suggests the possibility of countless universes, each contained within the subatomic particles of another, extending infinitely in both the macro and micro directions. This idea echoes the concepts of nested universes and the multiverse, topics of intense speculation and research in modern cosmology and theoretical physics. Observing the known universe and its governing laws reveals a similar pattern. It starts with elementary particles like atoms and ends with colossal celestial bodies and galaxies. Everything, from your lunch to newly discovered exoplanets, is composed of the same fundamental building blocks. The quest for a theory of everything aims to unite quantum mechanics with classical physics to understand the true nature of our universe and its potential beyond our current perception. The Big Bang Theory postulates that the universe originated from an infinitesimally small, infinitely dense singularity. This initial state, though incredibly small, contained all the necessary ingredients to build the entire universe. This is distinct from, but conceptually linked to, the idea of a universe arising from a single atom. String theory is another candidate for a theory of everything. It proposes that elementary particles are not point-like, but rather tiny vibrating strings or similar entities. The interactions of these strings would govern all known laws of physics, including gravity and quantum mechanics. However, string theory has shortcomings. For instance, it struggles to explain dark matter. Recent versions, such as one published in late 2018 by Swedish scientists, propose our universe exists on the boundary of an expanding bubble, implying more dimensions than the typical four and that our reality is just vibrations on the surface. Our civilization is a small part of this larger reality, potentially a single proton or quark within something far greater.